All right, so here I am again. Again, my name is Shannon Yee. I'm an associate professor in mechanical engineering. And for this next session, I'm going to be talking about organic and hybrid thermoelectrics. Right? This dovetails nicely into Seth's work with Stami and Cope and the whole other ecosystem here. And I promise I'm going to avoid any crappy puns. Okay, sorry. All right, so what we're looking at with organic and hybrid thermoelectrics is power generation and personal cooling. When you look at personal comfort, it really does increase a person's well-being, their quality of health, and their productivity. Right? It's very difficult to work in very hot and humid and uncomfortable environments. Right? Overall, we spend a large amount of energy, about 15% of all primary energy, just heating and cooling spaces. Right? I think the Candida building is a great example of how we can do that more efficiently. I love all the fans that I see. I love all the open architecture, and I know it's been designed well. But not all of our buildings are like this. Right? What if instead we had the ability to actually have personal thermostats? So I have a little example of a personal thermostat here. This is built by the company Ember Labs. This is called an Ember Wave. And what you can do is you can hit a button and it sends a cold pulse to your nerves and makes you feel cooler, especially if you're nervous about public speaking. And you can hit another button and you can make yourself feel warmer if you have a cold day. Right? Overall, this doesn't actually change my core body temperature. My metabolism does a really good job with that, but it gives me a sensation of feeling hot or cold. And this can be beneficial because if you look at a building, you can turn your Nest thermostat and expand that envelope a little bit, and a lot of energy can be saved if we just open up that envelope just a few degrees. So how can you make people feel more comfortable so they can be more productive? Overall, when we look at how we cool spaces, vapor compression technology is the dominant technology. We train every mechanical engineer in thermodynamics on how to develop power plants. Coal and natural gas dominate. How internal combustion engines work. We have cars, auto cycles, and diesel engines on the road. And we also train all mechanical engineers in vapor compression, right? That's a lot, right? It cools every house, every car, every refrigerator, every air conditioner, and it has some pretty detrimental refrigerants that we're using. Mostly, they have about a global warming potential that's several thousand times that of CO2. So what we're looking at with organic and hybrid thermoelectrics are, can we design polymers, plastics, that can actually perform this effect of taking electricity and provide cooling. All right? Thermoelectrics can operate in both modes of operation. I can take heat and I can generate electricity, or I can take electricity and generate cooling. They do this through an effect known as the Seebeck effect, where you basically take bulk N-type and P-type semiconductors and you run a current through them electrically in series, and then thermally they're in parallel and are actually able to move heat. And what we want to do is, rather than an inorganic device like this little watch unit here, can we actually make polymer fibers and integrate them into textiles? Can I make a shirt that heats and cools you? You can clip a battery to that shirt, and there we have a way of making people feel more comfortable and therefore improve the overall productivity and quality of health. So why polymers and why hybrid materials? The main driver for this is that polymers, as you probably know, plastics, have a really low thermal conductivity. It's right around 0.2 watts per meter Kelvin. A lot of the inorganic semiconductors that we use instead have a thermal conductivity between 1 and 10 watts per meter Kelvin. What this allows us to do is envision new device architectures, new device structures, like a shirt, that we can actually integrate these thermal devices and systems into. As Seth mentioned, a lot of these organic materials are quite scalable. We can envision making large area screens, large area textiles, large area tarps. And we have essentially countless synthetic combinations that we can work with. This is largely an underexplored area. There's a lot more chemistries to explore than we have knowledge of. And there's a lot of work we can do very much on the fundamental side of things. I get excited about this specifically for my research because there's a lot of new transport physics that we get to learn about. How does heat conduct in polymers? How does heat conduct in plastics? How does electricity conduct in polymers? How can we use that electricity to move heat? There's a lot of very fundamental questions there that I just enjoy exploring in my academic work. As an engineer, I look at this and I see there are a lot of new manufacturing processes and new device architectures to explore. So looking at the device physics, how does the device physics of a thermoelectric shirt actually work? And what we have here at Georgia Tech is we have a pretty robust community between a lot of folks working on organic synthesis, a lot of folks working on heat transfer, and I really like seeing the two communities come together. With that, one quick little thing I'll just make a note of. This summer, June 21st through 24th, Georgia Tech gets to host the 3rd International Conference on Organic and Hybrid Thermoelectrics right here on campus. The first one was in Japan, the second one was in Spain, and so I'm excited to have the opportunity to host the first one in North America. So if you're interested, that could be another opportunity. All right, thank you very much.